All right, a very good evening to all of you. So like I promised, we are going to look into the splitting of d orbitals in different molecular geometries, right? I'm not going to get into the basics because I'm sure that you might be familiar with the basics. In case you are not, you could like go to some other video and come back to this video, right? Over here, I'm just going to talk about how you can predict the splitting, because these kind of questions are quite common in the entrance exams, and for a general basis also you should know about these particular splittings, right? So before we begin, just a small overview, right? So when we talk about d orbitals, d orbitals are basically of five kinds, right? We have dxz, right, and dyz. Then we have d x square y square, dxy, and then dz square. All right, out of these, your dxz, yz, and dxy, right? Technically I should have written all these three together. They are basically interplanar orbitals. All right, what I mean by that is that if I draw an xy axis, so these orbitals lie in between the planes, right? They lie in between the planes like this, right? So you can think of like an angle of 45 degree. This is our x-axis, this is our y-axis, so they lie at 45-degree angle, right, approximately. So these are the interplanar orbitals, right? Whereas your dx square y square lies directly on your x and y orbital, right? Basically, how will it look like? It will look like this, right? It will lie directly on the x and y axis, whereas your z will lie on the z axis, right? So z axis, you can imagine that it is going from above the screen to below the screen. If you're watching it in a mobile screen, it is going from above the screen and going inside the screen. That is your z orbital, right? So you need to have a good imagination over here to imagine how the orbitals would be there. Similarly, if I talk about your xz and yz orbitals, so they will be basically somewhere over here. Like if you imagine this is the pen, so and if this is the z orbital, right, from above to below, this is the z orbital, so it will be somewhere over here like this, right? It will be somewhere over here like this, right? My finger is like in the, let's say, xz orbital, and this will be yz, right? So something like this, right? So this will be, so xy will be the plane of this pen, and then xz will be somewhere over here like that. All right, so this is the basic geometry of the orbitals. Now let's look into the different orbitals that we have and how they will split in different molecular geometries. I'm not going to talk about octahedral and tetrahedral. I'm sure many of you know about it, but quickly, if you like look into it, this is your octahedral and this is your tetrahedral. And octahedral will have dxy, dyz, and dxz, right? And then on top we have dx square y square and dz square, right? This is for octahedral, dx square y square and dz square. In tetrahedral, it just inverses, okay, it just gets inversed. So we have x square y square, and then we have dz square, and over here we have xy, dyz, and xz, right? So this is what the case is for tetrahedral, octahedral. I will later on, maybe I'll explain why this is the case for octahedral, tetrahedral. Let's just start with our square planar geometry, right? So if I talk about square planar geometry, you have to just imagine that the ligands, so there are four ligands, right? And all the four ligands are lying in this plane. That's why it's called square planar geometry. And now let's say if you have a metal in the center, any central atom, so the ligands are going to lie basically at 90 degree to each other. So basically what you can imagine is like if you just remove this metal for the time being and you just consider it as a dot. So one ligand is over here, right? One ligand is over here, one is over here, one is over here, right? This is how it's forming a square. So basically they are going to lie on the axis, right? They are going to lie on the x and y axis. So this is, let's say, your x axis, and let's say this is our y axis. So they are going to lie directly on the xy axis, because of which what will happen is that your orbitals which are facing which are basically having a xy geometry, right, which are facing towards the x and y geometry, they are basically going to have a lot of repulsion, because of which their energy will be highest, right? So dx square y square will have the highest energy because the ligands are lying directly on that orbital, right? Because dx square y square are basically on the axis itself, and the ligands are lying directly on the axis, right? Then it will be followed up by dxy. So even though your dxy basically is like along the interplanar axis, but obviously it will not have a direct repulsion, but it will have some repulsion, right, because of that. So that is why your dxy will be the next in line, right? It will be the second highest in energy. Now you don't need to memorize actually, or you don't need to really pay much attention to the ones that are in between the axes, like which are, sorry, in between the energies. You just need to know which is the highest in energy, which is lowest in energy for most of the questions, right? So most of the questions have been asked which is the most stable orbital or which is the least stable orbital, right? So generally the highest one and the lowest one, if you remember, that is, or if you if you are able to find out, that's good enough. But in the future they might ask you questions where they would want to test, like they could ask you a question, which of the orbitals is having just which of the orbitals is unpaired, right, in a d6 electronic configuration, in let's say in some geometry, which of the following orbitals will be unpaired, right? So then you might need to know the orbitals in between also. So it is not that difficult to find out the energies of the orbitals or to compare the energies. So anyway, let's look into it more. Now if I talk about xz and yz, so xz and yz basically are going to be like I told you. So if this is my plane and let's say the ligand is lying somewhere over here, then xz is like this, right? So it's basically, it's not facing towards the ligand. Now how among dz square and dxz do you compare? Now when we talk about dz square orbital, so it is basically in the z direction, but it has a small lobe. You can say it has a small lobe in the xy direction. Now because of that small lobe, because your dz square is basically a combination of dz square x square and dz square y square, right? It's a combination of both. So it has a small lobe in the x and y direction, because of which it has a little higher energy as compared to your dxz yz, which are basically completely in the z direction, and they are not facing any repulsion due to these ligands, right? So dz square faces some repulsion because of the presence of a small lobe or a donut shaped lobe in the xy direction, right? So that is why this is the energy for the square planar, right? I'll write down over here sp. Now when we talk about square pyramidal, here something interesting happens. Now in square pyramidal, what is the shape? So it's basically like it's basically like a square, but over here you'll have basically, like I can draw the same thing, ligand over here, here and here, and here you have to imagine that there is one ligand present, which is basically coming out of the screen, right? You have to just imagine one ligand which is coming out of the screen in the z direction. So now what happens is, now if I draw the x and y axis, right? This is your x axis and this is your y axis. So again your x and y axis will be of the highest energy, right? So your dx square y square orbital will be of highest energy because they are directly facing the ligands, and that to 4 ligands, right? Now what will happen is, what I talked about dxy, so the dxy was basically interplanar, right? So it was not directly facing any ligand, right? So it is facing some repulsion, but it is not a direct repulsion from the ligands, right? Whereas now if I talk about dz square, because of the square pyramidal shape, now one ligand is directly present in the z direction, right? Directly over, so it is directly present above the screen. You have to imagine there is one ligand present directly above your screen. So now your z square orbital will be directly facing some repulsion with that ligand. Because of this, what will happen? Your dz square energy would increase a lot, right? It will become greater than your dxy, right? So that is why this is the case over here, that in square pyramidal you have to remember that because of direct repulsion in the z direction due to the presence of the ligand, the dz square increases in energy, and then we have dxy, that is the one that is interplanar, and then obviously dxz yz we have at the least energy. So the only change that has happened from square planar is because of the direct presence of a ligand in the z direction, the dz square orbital has gone up in energy. All right, so I hope this is clear. Now talking about trigonal planar and trigonal bipyramidal. So this is quite interesting. Let's talk about trigonal planar. So let's say our metal is there in the center, and let's say we draw a ligand over here. So they are basically at an angle of 120, right? So let's just draw, they are at an angle of 120. So let's say this is in the y direction. This ligand is lying directly on the y axis. Let's imagine this, and then this is your x axis, right? So if one of the ligands is, let's say, at directly on the y axis, then the next one will be at an angle of 120. So this is how much? This is 90 degree. So 120 will be like around 30 degree. So this will make an angle of 30 degree over here, right? Because it is at 120. Then the next one is at 240. So 240 basically means, so from here if you go, this is 180, so plus 60. So that means that it makes an angle of 30 degree with over here, right? So you can see over here, these both ligands are at an angle of 30 degree from the x-axis, whereas this ligand is lying directly on the y-axis. So you know, directly on the y-axis we have your dx square y square orbital, so it will face a direct repulsion from there. But you also know that your dxy orbital is at an angle of 45 degree, right? It is interplanar, so it is at an angle of 45 degree. It is at an angle of 45 degree, whereas this ligand is lying at 30 degree, so it's lying very close to your xy orbitals, right? It is lying very close to your xy orbitals. So if you see the overall repulsion, because you have two ligands which are at an angle of 30 degree, whereas your interplanar orbitals, that is xy and your your xy orbital is basically at 45 degree. So it is facing considerably strong repulsions due to the presence of this ligands, not direct repulsions, but you can say somewhere in between, because it is at an angle of 45 and they are at an angle of 30, right? Whereas your x square y square orbital is facing one direct repulsion. So overall, due to taking both of these things into account, what happens is your dx square y square and dxy retain or have the same energy, right? Your dx square y square and dxy have the same energy. They are at the highest energies and they have the same energy, right? So that is why your dx square y square and dxy have the highest energy. Now how do you know that, whether you will have four energy levels or three energy levels? Because here we saw four energy levels in square planar and square pyramidal, but now we are seeing three energy levels. So basically you can think of it like that, that any molecule which has a d3h symmetry will only have three energy levels. Okay, a molecule with d3h symmetry, right? So this over here has d3h symmetry, because of which it will have only three three energy or levels, right? Three energy levels for the d orbital. I have explained this in my video where we relate group theory and splitting of d orbitals. So if you haven't watched that video, you will find the link somewhere over here on the top right corner, right? Anyway, so your dx square y square and dxy have the highest energy. Now what next? Next is basically if you compare now dz square and dxz yz. So now you have to see in the square pyramidal case, the ligands were directly on the xy axis, right? The ligands were directly on the xy axis. So I said that because your dz square has a small lobe in the x and y direction, that is why it will be of higher energy, right? But when we talk about this particular case, in this case there's only one ligand which is in the y orbital, which is in the y direction, and other ligands are in between the axis. So now what happens is your dxz and dyz gain energy, because you have to imagine this, that your dxz will be in the x direction but on top of this. So you have to imagine that it is coming outside the screen. Your dxz orbital is in the x direction but it is coming outside the screen. All right, just imagine it to be coming outside the screen. Just imagine that the orbital is just above the screen, right? So if this is your ligand, if this is the plane in which the ligand is there, it is just above this. Okay, it is just above this. So because of that, it is now facing considerable repulsion, whereas your dz square is not facing any considerable repulsion, because now there's only one ligand present in the y direction. But your xz and yz are having these ligands present, so they are just immediately on top of these ligands. So they face some kind of repulsion, because of which your dxz and dyz gain energy or are of higher energy, and dz square becomes the orbital of the least energy. Very similar is the case with trigonal bipyramidal, but now the only difference, and that's a very interesting difference, is that in trigonal bipyramidal what happens now, there are two other ligands which are above and below the plane, right? So that means they're lying directly on the z axis. If they're above and below the plane, that means they're lying directly on the z axis. So obviously the energy of the z square orbital will increase drastically, because over here, see, your dx square y square orbital was having only one direct repulsion, right? One direct repulsion. But now your dz square orbital in trigonal bipyramidal will have basically two direct repulsions. So that is why now your dz square becomes of highest energy, and then the same dx square y square dxy dxz dyz, right? So I hope this is clear. Now let's go to pentagonal bipyramidal. So this is very interesting. For pentagonal bipyramidal, what you can do is you can make ligands at an angle of 72 degrees to one another, right? So what we can do is, like, let's take x-axis and let's make one ligand on the x-axis, right? And then let's draw the y-axis. So the next one will be at an angle of 72 degree, right? The next ligand will be at an angle of 72 degree with this. Then the next one will be at another angle of 72. So overall angle will become 144. So 144 will be somewhere around like 135 will be exactly the middle. So this will be around 144, right? So you can imagine this as 144. This is the third ligand. Then the next one will lie at 216, right? Next one will lie at 216, right? If I'm not wrong, I hope my calculations are correct. So 216 would be somewhere over here, if I'm not wrong. So this is 180. So 216 will be 36 degree with this, right? This is 180. So it will make an angle of 36 degree. Then if we have 216 over here, then the next one would be at 288, right? 288 degrees. So this is basically 270, so 288 will be somewhere over here. So the next ligand will be over here, right? So these are the positions of the ligand, and then we have two ligands in the z direction. So obviously there is very high repulsion in the z direction, direct repulsion by two ligands. So that is why your dz square becomes of highest energy, direct repulsion, right? In pentagonal bipyramidal also there are two ligands on the top. Now you have to just see what is the scenario over here. You can see that in this case also, like one ligand is in direct, you can say it is in direct repulsion of the x orbital, right? Dx square y square orbital. This is also in direct, you can say in direct repulsion because it is at an angle of 72 degree. But now this ligand will be in direct repulsion of your interplanar, that is dxy, because it is at an angle of 144, whereas your interplanar will be at an angle of 135, right? Like at 45-degree angle. So this is at basically almost in direct repulsion. Then this one is also in direct repulsion of the interplanar axis, almost in direct repulsion. And then this one again gets in the your x square y square orbital, direct repulsion in the x square y square orbital, not indirect but like somewhat close to that. So overall, because of these things, the overall xy and x square y square have the same kind of you can say energies, right? Whereas then at last we have your dxz and dyz, right? So this is how the energy level goes for the pentagonal bipyramidal. Now let's look at some other cases. Now this is a very interesting case. This is your square antiprismatic geometry, right? Square antiprism, you can say, right? Now over here what you need to see is that it's quite interesting. So you can see that the orbitals over here are basically, it might look like it is having a d4h symmetry, but that is not the case. Okay, it does not have a d4h symmetry because you have to imagine this, that if you put an axis on the top, if you put an axis from the top over here, right, if you pass an axis through this and you try to cut it perpendicularly, if you try to cut the principal axis, or if you try to take this plane, then this molecule does not have any molecule down to reflect. Like you can see the 2D diagram also. If this is the ligand present at fourth position, then if I cut it perpendicular, if I take a plane perpendicular to it, then it is not reflected over here, right? So that is why it does not have a d4h symmetry, it has a d4d symmetry. So now what happens is, because of that, so you have to, let's imagine that this is our xz axis. Okay, let's imagine in 3D. So this is your x axis, and then like this is your x axis, this is the plane, basically this is the xy plane, and then this is your z plane, right? On top, this is your z plane. So this is the xy plane and this is the z plane. So you have to imagine now, this is your, let's say this is your dyz orbital, right? This will be your dyz, this will be your dyz, your orbital, dyz orbital, and this is your dxz. So you can see this is also dxz, and then behind this is dyz, right? So dyz, dxz, dxz. Now over here it is somewhere in between. It is not directly dyz, it is not directly dxz, it is somewhere in between xz and yz, right? So we have four ligands which are in direct repulsion of the xz yz orbital. That is why your xz yz are of highest energy. Now what else do we have? Now if you compare, we have dz square and we have dxy and dx square y square. Now how do we compare dz square and dxy and dx square y square? So your x square y square orbital will be like this, right, in the axis, and and basically let me just take another color, right? So this will be your dx square y square orbital in the x and y plane, right? Similarly, your xy will be somewhere in between the plane. So somewhere in between the plane means somewhere it will be somewhere over here, directly above this. Okay, directly above this. Similarly, your x square y square orbital will be directly under this. It will be directly under this, right? So your x square y square orbital will be directly under the ligands on the top, right? Whereas your dxy and your dxy will be basically directly above the ligands on the bottom, right? So this, let's say this is interplanar, right? And then your dx square y square orbital, basically these ligands are directly above the dx square y square orbital. They are basically directly above the x and y axis, right? These four on the top, they are basically directly above the x and y axis, and the ones over here are directly above these ligands are directly below the xy, the interplanar axis, right? So that is why your dxy and dx square y square also face a lot of repulsion, because four ligands are directly above or directly under it, right? And that is why they are of equal energy. And then at last we have your dz square orbital, which is not facing actually any repulsions. It is facing uniform repulsions from all the 8 ligands, right? Because the z direction is somewhere over here, right? So it is facing uniform. You can see over here, this is the z direction. So it is facing a uniform repulsion from all of them. It is not facing any direct repulsion. So that is why your dz square becomes of least energy. And now at last we have your a trigonal prism geometry, or trigonal prismatic also you can say. Now if you see the geometry over here, this belongs to your d3h symmetry. Okay, this belongs to d3h. So obviously you know it will have 3 energy levels. So now you just need to know what 3 energy levels will it have. So over here also similar is the case. You have to imagine this is the xz orbital. Okay, and then like this is your xy plane, right? This is your xy plane. So this will be xz, this will be yz, and not yz exactly, like they are also at an angle of 120 degree. So you can imagine this as a trigonal planar system, but above and below the plane. Okay, it is nothing but a trigonal planar system, but above and below the plane, right? So it will not be like, if you imagine this is dxz, it is very similar to trigonal planar, right? I told you one ligand will be in direct one ligand will be directly you can say one ligand will be directly in the xy axis, but the other two ligands will be at an angle of 120, right? So if I draw the x and y axis over here, then if one ligand is like over here directly on the y axis, then the next one will be at an angle of 30 degree over here, right? Similarly the next one again 120, so this is 210, so it will be at like this is, let's say 0, this is 120, so 120 means 30 degree with this, and the next one is 240. So again it will be basically making 240 means 60 degree with this, right? So you can see these two ligands are basically close to the interplanar axis, and this ligand is directly on the axis. So similarly over here, let's say if this is dxz, this will be somewhere in between the dyz, right? So like that you have to imagine it. So what does that mean? Like one of the ligands will be directly above the x square y square orbital, whereas one of the ligands will be directly above the xy orbital, right? Same is the case over here. So let's say two ligands will be almost directly above the xy orbital, and sorry, below the xy orbital, and then there will be two ligands which will be directly above the xy orbital, right? So like that we have to follow. So now what will be the scenario? That we have dxy, dx square y square, right? Which will be of equal energy but little lower than dxz, because you can see all the 6 ligands are basically lying in the xz axis or yz axis, right? So they will face the maximum repulsion. Then we have dxy, dx square y square, because the ligands are directly below or directly above these axes. And then at final we'll have dz square, which will be of least energy, because again over here also it will be facing a uniform repulsion. It will be basically over here, it will be facing a uniform repulsion from all the 6 ligands. So this is basically the geometry of molecular geometry, or how you can calculate the energies of different molecular geometries. And like one more thing, like for example, you can, so this is the way you have to just analyze it and calculate. The most important thing is that you should know the structure of these molecules, right? Similarly, if we talk about icosahedral geometry, so this is one geometry where all the d orbitals are of same energy. You can even check the character table of icosahedral character table, IH basically character table, and you will find that all the orbitals are of the equal energy, right? They all are having the same symmetry element. That means they are all of equal energy. So like I said, I have made a video comparing group theory and splitting of d orbitals. So if you want to watch that video, I'll give you the link. Just click on that I button and you can go ahead and watch that video, right? Anyhow, I hope you found this video useful. If you did, please give this video a big thumbs up. Also, do not forget to share this video with your friends, and do subscribe to the channel if you haven't already done that, right? And if you have any doubts, let me know in the comment section. I'll definitely try if there is some structure where you're facing some difficulty, some geometry where you're facing some difficulty, let me know down in the comment section, and I'll definitely try to help you out, right? Thank you so much for watching. I'll see you in the next video.
Hey guys, so I'm a verified educator on Unacademy, and along with that I'm also available on the Unacademy Plus platform, where I'm taking live classes along with other educators. So in case you're interested in attending the live classes, you can subscribe to the Unacademy Plus platform using my referral code, that is SETHI, and that will give you 10% discount. Alright, And in case you're not interested in attending the live classes, you can watch the free courses that are available on the Unacademy. For that, all you need to do is go to the Unacademy website or download the Unacademy Learning app and search my name over there, that is ACT. Once you do that, you will get the access to all the free courses that are available on the Unacademy platform. Alright, now let's begin with the video.